Good morning, everyone. If we could have everyone please take their seats, and we'll begin. Good morning. My name is Crystala Jones-Prather. I'm from MIT, and I'd like to welcome you to our Andreas Acrivos Professional Progress Award Lecture. Last year, I had the honor of presenting this lecture at the annual meeting in Phoenix, and this morning I'll be introducing this year's lecturer, Rachel Segalman of the University of California at Santa Barbara. I'll tell you about Dr. Segalman and her work in a moment, but first I'll give you some background on this lecture and the AIChE award connected with it. The Andreas Acrivos Award for Professional Progress in Chemical Engineering recognizes a mid-career chemical engineer for outstanding progress and service to the profession. The AIChE Foundation has endowed the Professional Progress Award in the name of Dr. Acrivos of the City College of New York. Dr. Acrivos is one of chemical engineering's foremost fluid dynamicists and one of the profession's most influential leaders. This award recognizes those who have made a significant contribution to chemical engineering through a theoretical discovery or development of a new principle, development of a new process or product, an invention, or distinguished service to the profession. Each year's recipient of the Acrivos Professional Progress Award is invited to deliver the following year's lecture at the annual meeting. I'll note that this past weekend, AIChE presented the 2023 Professional Progress Award to Hal Alper of the University of Texas at Austin. Dr. Alper will be invited to discuss his work, highlighted by contributions in synthetic biology and metabolic engineering, at next year's lecture. And now let's turn our attention to today's lecturer. Rachel A. Segalman is the Edward Noble Kramer Professor of Chemical Engineering, Materials, and Chemistry and Biochemistry at UC Santa Barbara. She was the Warren G. and Catherine S. Schlinger Chair of the Department of Chemical Engineering for 8 years, from 2014 to 2023. As the recipient of the 2022 Acrivos Professional Progress Award, Rachel was honored for her pioneering studies of functional soft materials, including semiconducting block polymers, polymeric ionic liquids, and hybrid thermoelectric materials. Prior to joining UC Santa Barbara in 2014, Rachel was a faculty member at UC Berkeley and Lawrence Berkeley National Laboratories, where she was also division director for materials science. In 2018, she became Associate Director of UC Santa Barbara's Center for Materials for Water and Energy Systems. She's also co-editor of annual reviews of chemical and biomolecular engineering and an associate editor of ACS Macro Letters. In her lecture today, Dr. Segalman will provide a window into her work and a discussion about charge-neutral polymer complexes as battery components. At the end of the talk, we will have time for a few questions. To participate, we ask that you please enter your questions for Rachel using the online system Slido. To use it, visit www.slido.com on your devices and use the hashtag AICHE. It's a lot of letters. Now, let's hear from our speaker. Please join me in welcoming this year's Acrivos Professional Progress Award winner, Rachel Segalman.
First, it is such a pleasure to be here. And on these kinds of occasions, I feel like half my job is to give you a science talk that I love, and half of it is to really say thank you to the community. And so I thought I'd do something a little bit unusual here, which is that I will get back to talking about the science and all of my wonderful, wonderful collaborators and my campus. But I thought I'd talk a little bit about how I ended up here and a lot of the thanks I have to give along the way. And I'm hoping that you will have patience with me as I go back over 100 years as I do this. I promise it won't take that long. And this is something some of you know about me, but many of you do not, which is that I have a strong tie to chemical engineering that goes back many, many generations. And it actually starts with the Boxer Rebellion in China. And so at the end of the Boxer Rebellion in China, the US and the European countries that helped put down the Boxer Rebellion demanded an indemnity fund from China. And the US realized that they were getting more money than they had spent on the war. And they said, you know what, this is not a great political stance. And so they established what turned out to be probably the first diversity and international student program. And they turned the money, that's what this won't work at all. That's what these New Yorker cartoons are showing, is that the US turned those into fellowships to bring students from China to the US to get particularly technical degrees, to a set of 8 universities that you can see down there. And they looked at the Dowager Empress of China and said, can you help us select the students? My great-grandfather was no one special. He was the son of a soldier. His younger brother was put up for adoption because the family couldn't afford to feed him. But he was the smartest kid in the village. And the village always made sure that if there was an educational opportunity, he got it. So they sent him to be tested. And this is the second scholarship class. He is the guy circled in red, and he won. So he was sent to Columbia in 1910 to get a degree in metallurgical engineering. The bottom picture is the day he took the test, and the top picture is in his sophomore year at Columbia. So that starts my family's connection to engineering, not necessarily chemical engineering. This was during the Chinese Exclusion Act. He couldn't stay in the US. He was meant to go back. He went back to China and said, my children need technical educations. The world is going to change. They need to have skills. And that included his daughters. So my grandmother, who's in the middle, and her sister were the only 2 women in their university. They were both chemical engineers. And my grandparents, who were in the middle of that picture, met opening a sulfuric acid plant together in the run-up to World War II, right? And so I come from this family with many generations of chemical engineering influence because of that one program that was started around 100 years ago. My mother and all of her sisters grew up in China. They all got PhDs in chemistry. And so I was lucky enough to grow up in a family where being a chemist or a chemical engineer was treated the same way as being a nurse or a teacher or any other profession. It was just one of those choices you could make and the things you could do. And so this is my huge thanks to a family where 75% of that family, most of them women, are chemical engineers, right? That is just part of the history and part of what I grew up with, which has been awesome, and I wish it were available to everybody. Continuing my little bit of thanks and a little bit about history, I also had the privilege of going to a lot of places where I had incredible mentors, both as a student, that's a picture of Peter Green up there, who was at Texas at the time, Santa Barbara with Ed Kramer, also my early faculty career at Berkeley, and now back to Santa Barbara again with an amazing family who I also owe a whole lot of thanks to for helping me get here and keeping me kind of grounded in what really matters in the world. This person, who has her face half hidden, is my daughter. She's a 17-year-old high school senior who says she wants to be a chemical engineer. If she does this, she'll be a 4th-generation female chemie. That may be the first for this community. So we'll see what she does. Okay. And I owe a lot of thanks to an amazing group of people, and both within my research group, showing a picture from back in 2004, as well as kind of very large, a picture from today, as well as this really, really inclusive chemie community that I hope I am a good part of and help to promote. Okay, so to the science. One of the things that's really framed my career has been in realizing that All of the energy transition applications require us to have a lot more control of transport through polymers. As an example, if you're talking about electrolyzers, solar fuel cells, or fuel cells, there is a middle part of this device that really requires you to be able to balance mass transport, proton conduction, gas transport, and frequently electron conduction as well, and to tune these independently of each other to get optimal performance. Similarly, if you're talking about batteries, and this is what I'm going to focus a lot on today, there is also a requirement for a balance of a metal ion conduction, in this day and age frequently lithium, along with electron conduction to help you run the electrochemical device. And as Crystal mentioned, my group has spent a lot of time thinking about thermoelectrics, where you're balancing heat and electron and sometimes ion conduction. And in all of these cases, including water energy nexus, the job is how do I control what moves through my material, and how can I design a material that does this efficiently? So for today, I thought I'd focus on just one subject, particularly in this case, lithium batteries. And because of the nature of this, I thought I'd talk a little bit about how the batteries work and what we need. And I'm sorry I can't point at things, but the idea is that the entire battery works on the idea of having reversible insertion of lithium ions from one electrode to the other. I think we're all aware that that requires an electrolyte through which your lithium ions can shuttle. That electrolyte needs to have high ion conductivity, needs to have higher voltage stability. Right now it's somewhat limited. And right now there's a lot of reaction with electrodes that create some capacity fade, which affects the long-term applicability of the batteries. And there's also some limited temperature stability and flammability. So for this reason, we're working a lot on trying to get the conductivities higher, also getting more of the conductivity to be carried by the lithium versus everything else in the system to get high rates. My group and many others have started working towards solid electrolytes, where they are inherently non-flammable, but have relatively low conductivity. And that creates a challenge of how can we make these better so that the overall device works better and could also be cheaper and more mechanically strong. But regardless of which electrolyte you choose, we still have other problems. One of which is that the cathode itself is not some monolithic metal. It's usually a composite of an active material, it has to contain lithium, but frequently containing other limited availability metals, along with a carbon additive to try and make this thing conductive, and some glue, right, called a binder, frequently polyvinylidene fluoride or something like it that's just a filler at this point, okay? If you keep up with the news, Inflation Reduction Act, all of these mandates, one of the mandates was to move to LFP-type active materials, lithium iron phosphate, because iron and phosphate are sustainable. They're metals that the US has a lot of and are not in limited supply, but that electrode material is a whole lot less efficient than the other cobalt and magnesium-containing alternatives. And so optimizing it to make this mess work has been a challenge. So why is that? This is a real battery made with the standard PVDF glue, along with carbon black and LFP. And what you're seeing at the top is if we charge and discharge this battery relatively slowly, it has okay capacity. But as we go faster and faster, that's the 6C, is 6 charges and discharges per hour, you see the capacity fades almost to the point where it's non-operational. And that's because the LFP electrode is really not as active as we need it to be, and all of the resistive losses are piling up. My group and many others have said, well, what if we replace the glue with something that's electrically conductive, right? So we go from polyvinylidene fluoride, which is just a glue, to something that is like a conjugated polymer. Can we make these things perform better? And in fact, we can. You can see that the capacitance is higher as we charge and discharge faster, but it's a little frustrating, right? One of the big problems is that it doesn't actually conduct ions very well, right? These conjugated polymers are not ion conductors at all, really. The other big problem with making that one-for-one replacement is that conjugated polymers aren't very soluble, right? And so in order to process this thing, we have to jump through a lot of hoops to get a very insoluble polymer to actually work here. So this ion conductivity is a problem, and they're really, really hard to process. But what makes matters even worse is that if we move to solid electrolytes, now we have a real problem with ion conduction. When we were dealing with liquids, the liquid electrolyte could kind of swell our glue and make it work. If you have a solid electrolyte, you're not going to be able to swell your glue, and that lack of ion conduction will become fatal to the overall device. Okay, so now we have a real problem as we move to solids. So what do you need? You need a binder that is processable, but isn't going to dissolve. A battery electrode that dissolves in operation is not where you want to go. You want it to be electrochemically stable, so the thing doesn't fall apart or stop working. It needs to be compatible with the other components, and it needs to have high electrical and ion conductivity, which are two different things. Okay? And that last piece turns out to be a fundamental problem, which is what I'm going to talk a lot about. Electron conduction, whether you're talking about in polymers or in other materials, really relies on crystallinity. In polymers in particular, it relies on your chains lining up well enough that you can get pi orbital overlap and get a charge to move from one side to the other. Ion conductivity in polymers relies on your polymer being able to move out of the way so the lithium can move. These are non-compatible requirements. One requires you to have some really rubbery goo that the polymer can move in, and the other one requires you to have a superstructured semi-crystalline polymer, right? And how do you optimize these things in concert? That's something that Michael Shabanik, who's a colleague of mine at Santa Barbara, and I've been working on for a long time, is starting to think about how can I make systems that are able to satisfy both of these rules. The easiest way to do it that my group has tried, as well as that of, you recognize a number of names, Shreyesh Patel, Christine Lescombe, Francesco Escobedo, is to just put something that looks like an electrolyte onto the conjugated polymer, right? Something that looks like an ether side chain to help you dissolve the salt and give you some ion conduction. The problem is that, at least in our hands, every single one of these over time starts to dissolve in the electrolyte. Because what we did was we increased the dielectric constant, we made it more similar to the electrolyte, and slowly the electrode starts to dissolve, which is not what you want overall. Okay? So that puts us in a corner where we have to start thinking about how do I get hierarchical order for the electron transport while also maintaining an ability to do ion transport. And that makes us think at multi-scales. We need an aromatic backbone that can conduct electrons. We need side chains or something that can help us move the ions through. We need to be able to get these to set up at a mesoscopic scale to transport electrons between the conjugated polymers, and also some mesoscale connectivity that will help us get charge all the way from one electrode to the other. So it's a very hierarchical set of requirements that we have. Okay? And this was our first attempt at it. Conjugated backbone will help give us electron conductivity. We add something that looks like an ionic liquid as a side chain, which allows us to tune the ability to dissolve salts like ionic liquids will let you do. If you look to the left, we get fairly good ion conduction. That's 10 to the minus 3 at various salt loadings with a good transference number. That is good enough to run a battery, actually. The right-hand side is the electronic conductivity, which isn't great. It's approaching good enough because we're getting some of the connectivity we need of all of those aromatic backbones to get charge from one electrode to the other. I'm not ending my talk here, so clearly there's a problem. And one of the big problems is not just electrical conductivity, it's that conjugated polymers have really poor solubility, right? And so what we did was we took an aromatic backbone, this is a group of chemical engineers, we added a very, very high dielectric side chain. That basically makes you a system that's soluble in almost no solvents on Earth, right? And so the result is that in best case scenario, using some solvents, we can get to maybe 1% solubility. But you don't want to be making macroscopic electrodes out of something that you can only process at 1%, right? It's not going to let you make something that is amenable to a battery. And as I said, this is a problem across anything you could think about with conjugated polymers. The backbone is rigid, it tends to aggregate, it's not soluble. We all add side chains to try and help with the solution, but typically you only get 1 to 3% solubility anyway. And that makes it very, very hard to make any kind of device that's not just a very thin film. And that was a problem when we were working on thermoelectrics. It's a problem if you're thinking about 3D printed electronics. We need something that will allow us to do solvent lean processing so we can make thick films, so we can make bulk structures anyway. So it's at this point that my group started looking around and thinking, can we take inspiration from elsewhere? Biological systems are frequently at very, very high solids loading of big polymers like proteins. And frequently how they do that is using electrostatics to the advantage. Take a polycation and a polyanion. The electrostatic interactions are attractive and pull the chains together, even if the enthalpy of mixing is very, very hard to overcome, right? And you can get some balance. You also get some entropic gain from letting the counterions go, and that's called a coacervate. And these coacervates can be up to 50% solids loading, right, in biological systems, usually in equilibrium with a supernatant phase that's much, much lower concentration. Biology, as I said, uses this all the time. This appears to be how membraneless organelles function, is by having disordered proteins coacervate in this way to make high concentration regions. Because I'm from Santa Barbara, it turns out muscle glues are exactly this, a coacervate of two differently charged proteins that allow the muscle to excrete something that's very high solids loading that allows it to glue itself to the piers and to other solid surfaces, right? So it's a process biology figured out really well. Can I use it in a contemporary system? My colleague Glenn Fredrickson figured out that, if I remove the solvent after I process it, those ionic interactions become extremely strong because the polymer backbone is actually a very, very low dielectric environment. That will even allow the charges to attract with 100 kT of interaction strength. And so it could be a great way for creating miscibility in systems that otherwise would not work this way. In fact, even at very, very low charge loadings, we can make completely immiscible polymers like styrene and silicone mixed together, right? So can we use this concept? So the idea is we take exactly the polymer I showed you a little while ago, which is an aromatic backbone with this ionic liquid-like side chain. We're going to mix it with a cheap commercial polyelectrolyte that is the opposite charge. And the idea is that we hope we would get to high solids loading by having these two things that are immiscible come together. We're going to dry it off, and then that very strong charge interaction in a low dielectric environment will trap the structure and make it insoluble later. Okay. It turns out that this system works really well in terms of coacervation. We actually get a huge phase window for coacervation, as you're seeing in this phase diagram, across a wide range of salt concentration, or polymer concentrations. If we don't add enough salt, the polymer will precipitate, right? It screens the interactions too much. And you can easily see the difference between a coacervate, which notably has really low viscosity because of the way the chains interact with each other, and high solids loading, and the precipitate, which ends up being a chunk, just like you would expect. Okay? And we can see the difference between these visually. Also, conjugated polymers tend to be deeply colored, and so we can easily see where we have the coacervate versus the supernatant, which appears almost clear. The other thing that's really neat is that the biological coacervate community knew that when you coacervate two chains together, it tends to stretch out the chain in order to maximize contacts, right? When you stretch out a conjugated polymer chain, it increases the conjugation length. You get a red shift in the optical spectroscopy, which is kind of cool, because what that indicates is we're able to transport charge or delocalize charge over longer distances, right? And that may be important for the overall performance of the system. We're getting an added benefit by coacervation, even at the first glance at these systems. So what we do is we take that low viscosity coacervate that's now 50% or more solids loading. We can now blade coat it. It just happens to be the right viscosity for us to blade coat easily. We make really nice dense films. They then cross-link together via the ionic interactions. We can do this on top of a substrate, with, for example, with electrodes, and dope it and start measuring electrical properties. And the first thing you see is that the bottom red dots are the conjugated polymer from which we made the coacervate. When we form the coacervate, the electrical conductivity goes up by a lot. See that all of the complex dots, the black dots, are a couple of orders of magnitude higher than the polymer from which we made it, right? On my best day, I might try to convince you that's because the chain stretched out and I got higher conjugation length. But even on my best day, 2 to 3 orders of magnitude is a huge improvement. It's probably not just that. In fact, if I plot it slightly differently and with better error bars, you see that it's frequently a lot more than 2 orders of magnitude. In some ranges of charge fraction, we're more than 3 orders of magnitude higher in the complex as opposed to the polymers from which we made it, in a system in which we've dumped in more than 50% insulator, right? So we've got 50% conductive loading and much, much better performance, right? And this is where skepticism should come in, right? Why does it do this? It should not do this. And so that's where we started looking back to see what else could happen. Many of our theory colleagues had predicted that when you make a coacervate, it's not just going to be a homogeneous mixture of your two polymers. There will be some structuring driven by the electrostatic interaction and the desire of the backbones to separate a little bit. That might make nanometer scale lamellae. It might make some kind of sphere structure, okay? And if we translate that to our system and we look at small angle X-ray scattering, we see a peak, right? And that peak is telling us we've got some nanometer scale ordering. I'm not quite sure why that's not showing up. Imagine those boxes had pictures in them. It's some red and blue phase separation with a domain spacing on the order of 4 to 5 nanometers. So it's making really tiny domains, kind of 2 nanometers-ish. Those of you who've thought about block copolymers, that's about a factor of 5 to 10 smaller than a block copolymer naturally segregates. It probably leads you to a cartoon that looks like this, where the chains are segregating into 2 different phases, red and blue. You have both interchain transport, where the electrons are moving along the backbone, and also the ability of charges to move between backbones. It's got to be that we are improving both the intrachain and the interchain transport in order to get this kind of improvement, and then also getting long-range percolation of all of the structures, right? All of these things have to line up to give us that kind of high performance across lots and lots of length scales. And we can actually probe that. One way to do that is doing temperature-dependent conductivity. The prefactor tells you about the high temperature conductivity limit, which tells you about the long-range conductivity of your system. The exponential, the activation energy, is telling you about the structural order. How well are the chains aligned? What is the conjugation length within them? When we do that, what we see is that the activation energy of the complexes is greater than the conjugated polymers we made them from by about a factor of 2. That's telling us that there is moderately higher structural order in the complexes. This is the same as me telling you the chains stretch out and are better aligned in terms of their energy levels. But we also see that high temperature conductivity is a lot higher, frequently orders of magnitude higher than the high temperature conductivity of the polymer alone. That's telling you that you're getting much higher percolation in the complexes, also that the chains are now being kind of forced together via that phase separation to make it easier to transmit charge from one chain to the other chain, okay? And hopefully you'll forgive the fact that we had to do a slightly different system here so you're not seeing all the cartoons. Okay, so now we have figured out why this coacervate works so well. Let's put it in a battery, as I tried to keep us all on time. The coacervate actually works really well in terms of electrochemical stability because it has those very, very stable ionic liquid type side chains as well as an aromatic backbone. So you're seeing by cyclovoltammetry, there's a very, very nice stable window relative to lithium. We think that combining that with enhanced electrical conductivity and the processability will give us kind of the ideal properties for a cathode binder. So what we're going to do is incorporate it with that LFP as well as the carbon additive. We actually don't need the carbon additive because the polymer is so conductive, but in order to do one-for-one comparisons, we're going to always throw it in. And we're going to hope that it improves both the kinetics and the rate performance. So this is what just a first attempt try looks like. We're comparing the blue, which was the data I showed you earlier of just the PVDF type binder, with that conjugated polymer binder. And you're seeing that at all rates, we have much, much higher capacity when we use the conductive binder. And also that it's reversible. If we go to a very high rate, like 6 charges and discharges per hour, then we go back to a slow rate, we're able to recreate things. And so we've got a very, very stable binder that doesn't seem to degrade with operation. But perhaps more importantly, this is again, blue is the conjugated polymer, orange is the complex, and this is potential versus capacity. We're running at much lower overpotentials in these systems. And what that's saying is because we have less resistance in the system overall, we don't have to charge it up quite as much. And by not having to charge it up as much, we're running a much lower risk of having adverse side reactions and parasitic reactions happening that would destroy the system overall. And so that's true at 2 charges or discharges per hour. At 6 charges or discharges per hour, PVDF stops working altogether. It's just not stable. It has to run at such high overpotentials, the whole thing degrades, whereas the complex keeps going. The result is that if you look at capacity as a function of time, these batteries with the coacervate binder are able to last for a very, very long time because we're probably running them at much lower overpotentials, so we have fewer of those parasitic side reactions. And just to kind of leave you with, that was a first attempt. There's a lot of space to play with this, right? What kinds of ionic liquids are we using as side chains? Which one of the commercial polyelectrolytes or homemade polyelectrolytes are we using as the partner here, right? And a lot of that has to do with trying to decrease the expense of these binders by throwing in commercial, relatively cheap stuff at least 50% of the solids loading. And this is just showing you that we're now starting to optimize that. That black data is the best one we've made so far, where it has really impressive capacity at very, very high charge and discharge rates. And you're seeing that we're running at very minimal overpotentials and maintaining that rate capability. Okay, so what I've tried to show you is that you can use these biological concepts like coacervation to make really highly processable battery components. The coacervation leads to improved electrical and ionic conductivity for reasons that make physical sense. And together, that mixed conducting binder dramatically improves battery performance, particularly in the next generation electrodes that we're going to be using in the near future. Almost all of this work was done by Gordon Pace, who is a graduate student in my group. A lot of the work on the charge transport, as I said, was a collaboration, a long-standing one with Michael Shabanik, work done by Lin Le, who now works for Apple. A lot of the NMR work I didn't have time to talk about is a collaboration with Raffaele Clement and her postdoc Pete Richardson, and I showed a little bit of theory from Glenn Fredrickson's group with whom I've had a very, very long collaboration. Of course, I'm just showing you a snippet of the kinds of things my group has done, but we owe a lot to a really amazing community that we've been part of. Thank you very much.
I'm trying to find Slido. I have to say, just as a personal note, I appreciate so much, Rachel, your beginning with your story. I think that oftentimes we forget that science and engineering and innovation is done by people, and people have stories. We'll be looking for your daughter.
She has a different last name. She gets some anonymity.
We'll find her eventually. All right, I have to put these on to read. So a question has come in from Slido. Why is the conductivity a non-monotonic function of charge fraction?
That's a really good question, and I'm not sure I can go back to it in this system. So what seems to happen is, and this is why I ratioed it over the conductivity of the conjugated polymer, is that it does seem to depend on the charge fraction of how much charge do we put into the conjugated polymer, and that then influences the mesoscale morphology. Why do you get such a big improvement at very high charge fractions? I can only hypothesize. My guess is because when we have very high charge fractions, the attraction between the chains is much stronger, and we're leading to somewhat better charge transport between the chains because we're compressing them. It's a, if you want to think of it this way, a nanoscale segregation effect.
Just remind everyone you can ask questions there. I will ask one question. I will also say I didn't expect to hear about biology in this talk, so I was very excited. You talked about scalability as being an important factor, and so with the materials that you've developed, what do you think is the processing limit in terms of what size battery you might be able to construct?
So at 50% solids loading, we're getting to the point where you can use existent methods for making electrodes. So it's not so much about size in that respect, although there are a lot of problems with the bigger you get, the higher the overpotentials, et cetera. It is more expensive than PVDF, right? It is still a new material, and that's always the challenge for chemical engineers, is it enough better to justify the expense of a new material? that's what we're working on now.
Yeah, so I'm going to ask a follow-up because I have the microphone. Are there, we see that often, as you pointed out, that you do have issues when you're introducing new materials. Are there particular entry applications that you're focusing on or that you would promote as a way to be able to introduce a new material with a new technology, so perhaps the sticker shock isn't quite as large? Are there specialty applications?
Yeah, I think that's generally the path for these kinds of new materials. It's probably still electrode materials, but looking for kind of niche applications to begin with, where you can prove scalability and prove performance. But there's enough difference in overpotential here that it may be worth doing anyway.
The first question was sort of a little bit of a different statement of what I just asked, which is how far do you think this work is from being in a commercial product?
So that's always a dangerous question to ask an academic because we're not always well-grounded in what does it take. What I'll say is that I'm a polymer physicist, right? Not a polymer chemist, a chemical engineer. What you're seeing are systems that we designed to be model systems where we could make a coacervate, figure out what it would take in order to improve the properties. Have we found the best system? Absolutely not, right? We showed conceptually that would work. Have we figured out in the end, the best system is probably not the one that performs best. It's the one that performs best and is easiest to make and easiest to process. We are at the pointy end of the stick on that one. Right? And so does that get done in academia? Does that get done via commercialization? Those are all debates for the ages. But I will say proving that something works and that it's a design concept is not the same as having a product ready to go.
I usually have a version of answering that question that says if I could predict the future, I'd have bought a lottery ticket.
Yeah.
And I'd be on a yacht somewhere and not here talking to
So what you've learned from that is Crystal is much more succinct than I am. But I fully agree.
How much do you think the mesoscale structure changes during battery operation? Is the 2 nanometer length scale structuring fairly static, or will it change?
So there are a couple things in here. One is that we've seen remarkable stability over time, so I do not think it's restructuring. And the ionic interactions they're aggregations actually, and they're frequently called ionic crosslinks. This is a well-known strategy. It's what's used in Surlyn, which is the coating on golf balls, to make it super, super strong. We're using those kinds of ionic interactions here. And so my suspicion is that it's not particularly mobile over time. Having said that, I showed you a lot of characterization we did of the material we made. When we actually put it in the battery, it became a lot more complex. We blended it with the active material. We blended it with some carbon black. We put it in contact with an electrolyte. It still performed, which was a minor miracle in and of itself. It performed well. But the structuring and everything else in that use application is actually quite different.
I hope a student asks this question. And you know students ask challenging questions, but students also ask very insightful questions. For someone who's thinking of going into this area, what are the grand challenges for the next 10 to 15 years? What are the open issues that there will be to explore?
Wow, that's a huge question. And it also depends what area you're talking about. I think one thing that may have been obvious from my talk and the way I think is that I'm a materials maker and a materials studier. I like to understand how the intrinsic interaction between materials can be used to change the way the materials perform. That is different than being a battery expert, which I am not, right? I do my best to understand what is the materials demand and how can we come up with new ways to help satisfy that. From my perspective on the materials side, there's a lot that needs to be done, particularly in the energy space, to both satisfy performance needs, particularly in transport, but also processing needs, sustainability needs, right? Everything from recycling capabilities, upcycling capabilities, as well as all of these transport problems having to do with energy. As you said, a lot of inspiration to come from biology. If I masquerade as a battery expert, I would also say there are a lot of big problems having to do with large-scale batteries that will require different chemistry. There are also a lot of problems having to do with sustainability and the fact that the batteries we have that work really well require elements that are not abundant and not easily mined or taken in the scales that we're going to need. And so there is a lot of space on the systems engineering side that is not my bailiwick, but hopefully there are a lot of younger engineers who are interested in it.
Can you comment on how the processing fluid mechanics might be used for the benefit of alignment of the conduction pathways? Is there room for further improvement? Actually, it says improv, but I think maybe it means improvement.
Yeah, as an experimentalist, I don't love improv. Yes, so when one uses the techniques we're using, which is doctor blading, smearing things on surfaces, you're automatically generating shear that is probably giving you some level of alignment of the chains for free, which may be helping you improve the system overall. That is really hard to study in messy systems. We know how to study it pretty well, very well characterized in systems that are a couple of components, well structured. But once you start looking at things like this that might have 3 or 4 components in them, kind of messy, it's hard to know.
Have you done any studies on polymer dynamics to see how strongly this correlates to the electronic and ionic conductivity in the complexes?
So electronic conductivity is notably, generally, not coupled to polymer dynamics. It kind of relies on your chains being well aligned and somewhat static in their arrangement. And this is part of why designing these kinds of mixed conductors has been so hard, because ionic conductivity is directly tied to the segmental motion or the dynamics of the polymer backbone. And trying to get both a static pathway set up and a dynamic pathway set up simultaneously is hard. In these systems, the ionic conductivity absolutely scales with glass transition temperature, which tells you it is tied to the dynamics. The electrical conductivity is Arrhenius and ties to this high temperature plateau, as well as the kind of activation energy that correlates to percolation. And so, yes, this system is not unusual in that way. It absolutely has those two kind of competing design requirements built into it. It's just one way to solve that competition. I have to say, it's really weird getting all of your questions from one source.
from a very unknowledgeable source, right? Am I pronouncing the words correctly, Rachel? I think I'm doing okay there.
It's like you guys are just watching a dialogue between me and Crystal, the voice of many people.
I'm standing in for all of you. I hope I'm doing okay. Next question. People are beginning to explore sodium batteries rather than lithium-ion ones. Will the materials you're exploring be suitable to sodium-ion transport as well?
So this is kind of what I was alluding to, that forget the cobalt and the other components of a lot of the lithium batteries. The lithium itself is not a particularly abundant resource. So moving to things that are much more abundant, like sodium, zinc, copper, magnesium, are all kind of on the table at the moment. And the question has to do with, is the voltage stability window of these materials broad enough to support those? And that's not something we've played around with enough. Furthermore, even understanding how ion conduction happens in the multivalent versions, right? Sodium is an abundant monovalent choice for a future battery. But a lot of the multivalents are of interest right now because they'll have higher power densities. And trying to figure out how to get multivalent ions to move through the electrolyte is an interesting frontier. My group has thought about the ion side of it, making electrolytes. We have not yet really thought about the mixed conduction side of it and if it will be different.
There is a lamellae structure. May I ask, is there a block that selectively wets the LFP particles?
So this is a little different because these are not block copolymers. They are coacervates. It is possible that one of the two components of the coacervate wets the LFP. It's hard to know given the messiness of the system. It's also hard to know whether that's an advantage or a disadvantage, to be honest, right? You want ion and electron conduction, and your components are doing the opposite parts of that job.
Can you comment on the crystallinity of the new complexes and its effect on conductivity?
So crystallinity is an interesting question. In those cartoons that I was trying to show you, some of which were appearing, some of which were not, I was showing you that the domain spacing of these red and blue phases that we're seeing are on the domain spacing is 4 to 5 nanometers. That means that the phase is about 2 nanometers wide, right? 2 to 3 nanometers is a couple chains, right? It's not very large. It's enough for a chain and another chain to communicate with each other, to pass a charge between them. They seem to percolate. It's kind of amazing that they do. But it's not so much that this idea of crystallinity, which is really a more macroscopic idea, has a lot of definition in that very, very small region.
You focused on transport properties. How do you characterize binding properties? And binding was put in quotes here.
So the binding properties have a lot to do with mechanics and how well does your system wet, how well does it hold all of the pieces together. The kind of nice thing about these coacervates and all of the ions around them is that they do a really good job of adhering to a lot of the components that we're putting inside. And so we've seen no problems with this. We've seen no interfacial cracking. We've seen no incompatibilities. They seem to help us disperse the active materials really well. But have we studied this a lot? That is actually something we need to look at going forward. And is probably one of the things that will be necessary as you think about maybe commercializing, maybe going somewhere else with it.
How do these polymers impact SEI layer formation on the electrodes? And can you explain what SEI is for the person asking the questions?
So the SEI layer is the interface between the electrolyte and the electrode, right? It's that solid electrolyte interface. Okay. And notably what happens when you turn on a battery is that you're applying a fair amount of voltage, and there is some chemical reaction that happens between electrodes and electrolytes. It's been very, very finely optimized in a lot of kind of more mature battery systems so that it is not just a bad layer, it's actually something that helps promote stability over a long time. So frequently batteries are pre-cycled to make an SEI that is beneficial to the system as a whole. Absolutely, anytime you change little bits and pieces of the system as a whole, the SEI will change and would have to be reoptimized. The fact that these help you really bring down the overpotential probably means that you can have fewer of those kind of side parasitic reactions. But as I said, the SEI isn't always a bad thing, and so the reoptimization will be necessary if you were to use this kind of binder.
You have generated a lot of questions, Rachel, which is a wonderful sign for an important area and a very engaging talk. Is anyone from
in here like typing in questions, or are we all just watching the stuff come in from the outer world? Okay.
Someone's typing something. Have you studied the dielectric properties of these systems and how that may affect the different types of transport?
So, the fact that we have ions, the positive and the negative charges in the polymer probably drive up the dielectric constant by a lot. It is notoriously hard to measure in these kinds of systems because we have so much ionic conductivity happening at the same time, right? And so we have not looked at that a lot, but the whole premise is that because we have those complexes, those charge-neutral complexes, they've driven up the dielectric constant, they've made it easier for us to solubilize lithium ions that can then move through the material. And that's why we have ionic conductivity even without electrolyte around.
Okay, this is going to be the last question because Rachel has been extremely patient and extremely informative. What is the relationship between the electronic conduction and the carbon black, which we generally rely upon, and the electronic conduction through the polymer?
So I didn't get into this for sake of time, but the polymer doesn't actually need carbon black in there. The batteries operate approximately the same way with our conjugated polymers without the carbon black. Because they're so electrically conductive, you don't need that additive. But I wanted to show you comparisons to PVDF. The only way to do a one-for-one comparison is to have the PVDF function. The PVDF only functions with carbon black. So we put carbon black into both of them, so I could show you a one-for-one comparison, but this binder system doesn't actually need that component there at all.
It's a perfect question to end on. There was like a little extra nugget at the end. Yeah. Let's thank Rachel very much and congratulate her again for being the 2022 Acrivos Professional Progress Award lecturer.
Thank you so much.
Sorry. I can't read the rest of it from my phone. I have to come back up here. Okay, so just a couple of final notes before we adjourn. First, the annual meeting's next featured... It's on? There it is. The annual meetings, our annual meeting's next featured lecture is this evening's Daniel I.C. Wong Award Lecture. That lecture is organized by the Society for Biological Engineering, and this year's presenter is Suimin Zhao of the University of Illinois at Urbana-Champaign. In his talk, Dr. Zhao will discuss the dawn of a new era in synthetic biology. That takes place this evening at 6:15 right here in this room, Ballroom G&H. I'll add that tomorrow's program features 3 major lectures, namely the Prausnitz AIChE Institute Lecture, the James E. Bailey Award Lecture, and the William R. Showalter Lectures. You can find details about those lectures using the program app, and we hope that you'll be able to join us. I'll also mention that our expanded program track devoted to inclusion in our profession continues both today and tomorrow. Among the many opportunities for engagement, you'll find events and discussions hosted by our Women in Chemical Engineering community, our Latinx and Chemical Engineering community, our LGBTQ+ group, and others. Everyone is welcome, and I encourage you all to take part. Finally, I'll note that today is the last chance to interact with our annual meeting exhibitors in the registration area. Our exhibitors and meeting sponsors play a very important role in making this meeting happen, and we are indebted to all of them. I hope you'll take time to meet with some of them today. With that, we do conclude the session. Our next program block begins at 12:30, and whatever the day brings for you, wherever it takes you, I hope that you have a fantastic conclusion to the annual meeting. Thank you.